Hi everybody, this is Chauke again, facilitator of building and structural construction in 6 at Majuba Tibet College. I will be taking you through moment of inertia. So this is part 1B of our video. You remember that we did in part A, we did the position of the centroid. All right, so now we'll be focusing on number 2, which is the moment of inertia. All right, you remember the question or our diagram is this one, given the I section 203 by 102 and our channel, which is inverted here along YY axis, which is 180 by 70, and we discussed this distance is the position of a neutral axis, which is 144 from here to there, after we have located the position of individual neutral axis or neutral axis of individual sections, which is 101.6 and 192.7, whereby we said we took the whole height of I section, we added the T1 of channel, and then we subtracted 19,2 to get this 193. Yes, so we end up getting one of 144 or 143,5. That is the position of our neutral axis. Going forward, the moment of inertia, which is number 2. So this is also a little bit straightforward, but how do you go about it? Number 1, this information you'll be given, or we can locate it right from our steel table. So for I section, the inertia for I section, let's go here. All right. Let's come here. Let's move this here. All right. So for our I section, which is I section tapered, which is 203 by 102, the inertia is gonna be here about x-axis 22.97. Mind you, our I section is seated like this, upright. All right, so that is very important. It is seated by its x-axis. All right, x there. If we can look at this diagram from this side here, x. So that's how our I section is seated. All right, so it's very important, and because of that, now we can come and look at under x-axis, which is inertia. If this was flipped to sit along y-axis, okay, if it were to be flipped like this, along y or y-axis be on the horizontal, what's going to happen is that your inertia, you'll be required to look at to look at it from your y. Okay, so that's very important. So here our inertia is 22,97, right? So we can go back to our slide here, which is this one. All right, so what do we have? 22,97. all right, and then what about our channel? We will go to our steel table. Channel, remember, it is 180 by 70 by 22. Now our channel is, if it's upright like this, your x and your y. So but if you realize our channel is not upright, all right, it is seated by your YY there. So that is a very important thing then, that you're not gonna come under XX to locate your inertia. You'll have to go to your YY axis to locate your inertia, which is 1.135, because your channel is no longer upright. All right, your channel is no longer upright. So now you're not gonna go to XX to locate your inertia. If it was upright like this, you will go to XX to locate your inertia, but now it's no longer upright. You have to come here, all right, to YY, which is 1.135. Remember, multiply by 10 to the power minus 6, all right, meter to the power 4. Okay, so now this it is here. Can you see? All right. So now that you have located your initials, very easy. You just add this one, and then you get 24.105 multiplied by 10 to the power minus 6. All right. And then you have to locate your H distances. So what will be your H distances? Let's see. Your H distance now, it is a distance from your neutral axis to YY. All right, so now your line of reference will change. It's no longer going to be this one where your beam is supported, but it's going to be your neutral axis. Your line of reference now will be your neutral axis to your centroid of your specific section. All right, so your H for your channel will be from here to there, about YY, and then your H for your I section will be from your neutral axis, which is our line of reference now, to your XX. All right, from here to there. All right, let me use this pen here. Okay, from here to there, that is your H1, and that is for your I section, and then H2 is going to be from here to there. All right, so how do you go about it? You take your D, which is this one, all right, and then subtract your Y, all right, and then you'll get your H. Again, you'll take your D for your number 2, and then you subtract your Y, all right, and then you'll get this one. So your answers must not be negative. Now these are just distances, all right, so you can just take the bigger number, subtract the smaller number, but either way it does not matter. But your answer should not be negative, or should not be left in a negative form here. Okay, so now the next step is to take your area. Let's go back to your area multiplied by your H squared. Here's the formula here. All right, your area 2,797 multiplied 10 to the power minus 3 times 0,048 squared. All right, so you get these two values here, and then you add them to get your sum. Okay, and then your initial about XX. Now this is the combined inertia. All right, this is the combined inertia. You will have to add the two. All right, let me make a point now. Let's say you're given a plate instead of your I section, just or your sections, which you can find them from your steel table. Let's say you're given a plate. All right, how will you determine your inertia? All right, because you're not going to get the value for your inertia from your steel table. All right, how will you go about it? You will have to use the method from N5. All right, so because a plate is a rectangular form, we've seen a rectangular form, you will say BD to the power 3 over 12. Make sure that your values are in meters. Okay, don't convert after you've calculated your inertia, but rather put your values in the formula in meters already. Okay, so that's how you calculate the inertia if you are given a plate. Again, it's going to be what? BD cube over 12. That formula that you learn from N5. That's how you do it. But for these sections here, because we do have the properties of these sections right in your steel tables, we just went there and then we plug them out. Easy like that. All right, and then we determine the total, and then the total. So this is the inertia for the combined sections of our compound beam. Okay, now let me see if we can go forward. All right, let's just do number 3. All right, maximum moment of resistance. Maximum moment of resistance. Now that we have our inertia here, we can calculate maximum moment of resistance by saying ZE is equals to I over Y, this formula here. So this one will be your inertia, and this one will be your the value or the height of our centroid from the line of reference. All right, so our inertia is what? 36 10 to the power minus 6, and then the value here, you remember, it is this one. Okay, so you can just say divide the 2, you get this value 251.63 multiplied by 10 to the power minus 6. Okay, and this is your section modulus. You need this value to calculate the maximum bending moment. Here's another formula for section modulus. All right, bending moment over the maximum allowable bending stress. So we're gonna make bending moment maximum our subject of formula by multiplying these two here. All right, so remember ZE to 51 over 10 to the power minus 6, which is this one, and then your PT you are given from the formula from the equation. Remember, bending stress is 165. All right, bending strength is 165. So MPa, so it's gonna be 165 multiplied by 10 to the power 6 Newton per meter square. So MPa is Newton per millimeter squared. Remember that. So because our moment is gonna be in kilonewtons meter. All right, and our ZE is cubic meters in meters. So we want to convert Newton per millimeter squared to Newton per meter squared. Then you have to multiply that value by what? 10 to the power 6, which is a million. And then you multiply the 2, and then you get 41.52 kilonewtons. So the answer that you're gonna get here is gonna be Newton meter. So you divide it by 1,000, you're gonna get what? Kilonewtons meter. All right. So that is our moment. All right. Let me deal with this question now. Now this is the maximum uniformly distributed load. All right, the maximum uniformly distributed load. You remember that our beam. Okay, so UDL, the maximum bending moment for UDL, the formula is given by our WL squared over 8. All right. WL squared over 8. So this is the formula for what? For the uniform, for the UTL, or bending moment for UTL. If it was a point load, it was the moment for point load is what? Is PL over 4. So UTL WL squared over 8. So we're gonna make W, which is gonna be W total, actually total load. It's a formula. So 8 multiplied by this one here, and then divided by L squared. So here's the formula. We made W the subject of the formula. Okay, and then 8 multiplied by 41, which is our maximum moment, the one that we've calculated here. Okay, 41.52 kilonewtons meter. All right, there should be meter here. All right, kilonewtons meter. It should be kilonewtons meter here. Let's just correct this one here. Okay, right. Now we will say, okay, over the span we're given, which is 5,3 squared. All right. Now, because this one is gonna square even the meters here. All right, so the meter will cancel with the meter here. We're left with 1 meter at the bottom because of this square, and then the answer would be 11,82 kilonewtons per meter now. All right, so here don't bother about converting kilonewtons to newtons, because you're still gonna divide it by 1,000 to convert your the newtons to kilonewtons. So just take it as kilonewtons meter, and then the value that we're gonna get here will be in kilonewtons already. So kilonewtons per meter. So that is your maximum uniformly distributed load. Your maximum UTL is gonna be this one. All right, guys. Let us pause here, just to make sure that this video is not too very long, and then just watch the C part. That will be the last part of our video. All right, thank you very much. Stay tuned.